Taking part in this press conference, we have Adam Dingwall, who is a doctoral student at the Department of Earth Sciences at the Uppsala University in Sweden. Jorn Zesterhan, who is the head of the Computational Fluid Dynamics Group at the Technical University of Berlin in Germany. And Joe Michalski, who is an Aurora Fellow at the Earth Sciences Department at the Natural History Museum in London. You can start, Adam.
So, this is yours?
Okay, so our study has been about the probability of exposure to high concentrations of volcanic ash over Europe. And this is mainly from an aviation point of view, why this would be interesting. So, let's just... we all remember the Eyjafjallajökull eruption back in 2010, which caused this widespread disruption of air traffic all over Europe. And I guess everyone has their own story about it, everything from very dramatic to something as a petty annoyance, which was my case. I was working on my master thesis in atmospheric dispersion in urban environments. And one of my supervisors who had was supposed to provide me with data I needed to get on with my project got stuck in a foreign country on an airport. So that was a bit annoying. But there was seriously more problems with than that, of course, and then maybe even people in this room had problems with it. But that inspired me to get into looking more into this and trying to figure out what is the probability that something like this happens again in the future. So when I got my position that I'm at now, we wanted to look into this, and we determined that the best way of doing this is to try to use the same methodology that is used by ash forecasters, so in those volcanic ash advisories that are issued in the event of an eruption, which is using models to try to describe the transportation of ash in the atmosphere. The main difference being that instead of looking at a specific case, we're trying to look at many different possible cases and many different possible conditions in the environment. So if we take one of those eruptions and we try to simulate the dispersion of ash from this volcano for many different weather conditions. This is the result of tens of thousands of simulations of the same eruption. We can say something about which areas are most likely to see high concentrations of ash as a result of this eruption. So what we see from this is the first 2 days following an eruption that is roughly 10 times more intense than the Eyjafjallajökull eruption, and that's because it's a good illustration. And we can see that the areas that are mostly affected is the Scandinavian countries and also the northern UK. Now, this is for an eruption that is not restricted to any specific time of the year, but we can also look at an eruption for restricted to winter months. So this is December through February. And you can see that the cases are very different. So in winter, we have a much stronger eastward transport of the ash, and we have a much higher probability of exposure over most of Scandinavian countries and also over Central Europe. So the reason for this is because the westerly winds which dominate these latitudes, they become stronger in wintertime because of a stronger temperature contrast between the equator and the pole. And this is what is driving the whole weather system. But if we get back to the main question here, like the Eyjafjallajökull eruption and how likely this is to happen again. So we can do the same thing for that eruption. And then we end up with something like this, which looks... the first thing we see here is that the probability of actually even reaching mainland Europe is very low. So what this tells us is that the eruption that we had in 2010 is unlikely to cause the widespread disruption that we all experienced. But we all remember that this happened, so either something has changed or this was an extremely rare event. And to some extent, both of these answers are correct. So we had quite uncommon weather conditions in end of April 2010, which allowed the transport of ash directly over the European continent. But that alone does not explain this difference. So the main difference is that there was a change in the procedures for the volcanic ash advisories. Prior to 2010, there was a zero tolerance for ash. So if there was any ash detected in any possible way, you would cancel flights for that specific area. But practitioners didn't really like this method because it caused a lot of shutdowns of airspace. So they decided on a threshold value. So as long as the concentrations are lower than this, it should be safe to fly. And that's the method that we've been using. So this reflects how the new method estimates the hazard. So But we have also been looking into how much the choice of threshold affects the outcome. So we can adjust the threshold value to a little bit lower or a little bit higher. Here we've been adjusting it by a factor of 10, and the reason why we've chosen this is because that represents about the uncertainty in the data available to the forecasters in a real-time event. So this is about the uncertainty in the forecasts would be about the same here. But as you can see, it has a very strong influence on the outcome or on the results. On the other hand, if we look on a large eruption, so the first eruption that I showed you examples from, it has hardly any effect at all. So unfortunately, this puts us in a position where the weakest eruptions or the most common eruptions are the ones that will provide us with the most uncertain forecasts, whereas stronger eruptions will give us more accurate forecasts. But bottom of the line, we can say that an eruption with the characteristics of the one that we saw in 2010 is very unlikely to cause the same shutdown of European airspace as it did back then with these new revised methods.
Okay, it's my turn now. Okay, just a second. I need to do the paperwork here. So good afternoon, ladies and gentlemen. Before I start, I would like to play a sound for you. So what you just heard was not what you saw in the picture. What you can see in the picture, this is a jet engine, and what you heard was this one. What you heard was a volcano erupting, and the fact that it sounds very much the same is what we would like to use in our work. So we would like to find out what the sound of a volcano is telling us about the ash which is coming out. So if you look at a volcano, and I hope you can see this in the pictures over here, on the left-hand side, or is it left-hand side? Yes, left-hand side, you can see a picture of a volcano, and you see mainly ash. And on the right-hand side, you see the result of a numerical computation, and you don't see the ash. It's a density gradient. And what you can see is that there are a lot of structure inside the jet, which resembles very much, of course, the other jet you have just seen. It's this one here. What you can see there are shock cells, and the interaction of those shock cells with the ambient air and the turbulence going through these shock cells is what is one part of is generating one part of the dominant spectrum in these jets. So this is what we can hear. And the reason that a jet is a jet, this is what I have written in the top of the slide, basically helps us to understand from an engineering point of view how much ash is coming out. And this is exactly the same what Adam was talking about. We would like to know how much ash is coming out. And you can imagine that it's not very easy to go to a volcano and put in some measurement devices and measure the ash. It's not even easy to measure the diameter of the jet vent, because you can see nothing but ash. So, but you can hear. So this is the basic idea of what we do. And what you can see here is a numerical computation of just the starting of one of those jets. And not very well visible in this picture, but believe me, what the sound waves are tracked. You can see the front tracking here, and the sound wave radiation direction is strongly depending on the source of the sound, the strength of the initial vortex, the strength of the shock cells, and the ash content. And so this is basically what we like to do. We try to find out from numerical computations and comparison with the experiments in the field how much ash is coming out and how we can compare it. So this is a quantitative comparison. The black line is basically saying one eruption from Stromboli, the one we have seen before, and the red one is one of those computations, properly scaled. We are very happy with this result, and we can also, in this picture, try to localize the sound sources. What you see is results of a beamforming method. This is a specific method to find out the source of the sound from the recording of the sound with a tons of microphones, sometimes up to 100. We used only 8 here. This is why the result is not very good. but still we are quite happy with it and could localize the sound and could quantify at least the velocity and the diameter of the wind. So thank you very much. Wait, I have to do something.
Okay, great. Thanks for coming. This is a presentation about volcanism on Mars. And, well, remember, the atmosphere of Mars is about less than 1% as thick as on Earth, so I don't think volcanoes would sound as cool on Mars. But they are, in fact, very interesting. Do you mind to do the clicking? Okay, one more, please.
I do the clicking.
Okay, great. So, and what causes an explosive eruption? It's magma that rises up near the surface of the planet, and the gas that comes out of the magma creates bubbles which will ultimately explode and create a fragmentation of the magma at or just below the surface. So that's a process that occurs on Mars as well as on Earth. And what's interesting is that Mars has some really key differences from Earth which affect whether volcanism will be effusive, that's like the slow eruption of lavas. If you get injured by one of those, it's kind of your fault. Versus the more explosive kind of eruptions that we've heard about already. Now, on Mars, most of the planet is basaltic. It's a mafic iron and magnesium-rich lava, which is typically associated with volcanoes that are not so explosive on Earth. So it's a little confusing then when you hear about explosive volcanism on Mars. Well, Mars is basaltic. I'll explain the connection later. It has a lower mass, which means there's lower gravity, which means there's lower pressure in the crust. So as a magma is coming up through the crust, it's under less pressure. And it also has lower atmospheric pressure. So not only would it affect the sound of a volcano, but it actually affects how the gases are expelled at the surface. So one more, please. Now what that means is that basaltic lava, which with a typical amount of volatile content, volatiles are just gases of any sort, don't worry about that, but as basaltic magma comes near the surface on Mars, because of the lower pressures, that magma can fragment within the crust and sort of blow itself up. That's predicted by theory. We think that we see evidence for that. So in this presentation, I'm giving an update about supervolcanism on Mars. Now this is a volcano which probably makes some volcanologists cringe a bit because it's not a formal term. We use it to communicate large eruptions. And on Mars, a lot of these eruptions are likely to be large. But what it also means is eruptions that are dominated by explosive activity, that are catastrophic, create huge amounts of ash, and really create structures that are dominated by collapse instead of building up of a mountain in the central edifice. So because on Mars, lavas, even basaltic lavas, can be more explosive, we think it's reasonable that you would have a type of supervolcanism on Mars, which has some of the same characteristics as what you see on Earth. And what does that mean? Well, on Earth you have in the middle of plates or within plates, you have giant magma bodies that have erupted in the past and created huge deposits of ash. Those are a more silica-rich composition on Earth than basaltic, but that's not really what we're talking about. We're talking about basaltic ones on Mars that create huge catastrophic eruptions. Now, on Mars, looking backward in time, the most recent volcanoes we see are dominated by small vents. As you move further back, we see large shields, which are similar to what you find in Hawaii. And moving further back, we've known for a long time about some elements of explosive volcanism. But what we've seen recently, next, are that in some of the most ancient terrain, we see craters which are not actually impact craters. There are lots of impact craters on Mars, but there are some holes in the ground which are not impact craters. They were formed by collapse and explosive volcanism. One more. And here are a number of examples of those. So this was originally published 6 months back, and we've given an update this week that we see even more candidates before. So far, the candidates are numbering in the tens, not in the hundreds or thousands, but enough that we are feeling confident that we found a very different type of landform on Mars. The best example is one in the top left there. That's called Eden Patera. But as you can see, in a number of these, in all of these cases, you see depressions in the ground at the scale of tens of kilometers, which have linked depressions and various structural features indicative of collapse of the terrain. And then nearby those features, oh, sorry, we'll get to that in a second. That's important. No, we actually will continue. And these are important because we didn't recognize this kind of volcano before. They would erupt lots of ash, but also gas and lavas as well. And that's interesting because if you look at this graphic, this shows you a difference in the modeled prediction of volcanism going backward in time, from the recent up until 3 and 4 billion years ago. The top line is the predicted amount from the thermal modeling of magma production. The bottom one, and this is an exponential scale, the bottom one follows sort of roughly the same pattern for the last 3 billion years, but before that, things are totally different. We don't see a lot of evidence for ancient volcanism. So people have wondered, has that all been removed by erosion, or is it because we're missing something? So we think this new category of volcano could help fill that void, where we understand that maybe some of the earlier volcanoes on Mars were more explosive, and that's why they haven't been recognized as easily. So if we're able to map out more of those in the future, then it will help to align these two lines so that the predicted and the observed are more in tune. And lastly, a lot of the layered deposits that you've heard about on Mars, where there are these sedimentary rocks, also a lot of altered rocks, sulfur-rich rocks, fine-grained fragmented rocks, that stuff is composed. It represents hundreds of thousands of cubic kilometers of material throughout the equatorial region, and we don't know where it came from. The association of that material with some of these proposed supervolcanoes suggests there could be a link, and we think that some of the modeling that's going on right now actually shows that you could produce that material from the eruption sites of our proposed candidate supervolcanoes. So it's interesting as far as future rover exploration. It's interesting in terms of understanding the planet dynamics and so on. And that's it.
Thank you very much. I think there was already a question at the back. Christina, do you want, or... Yeah?
To whom?
Thank you. This was a question to Jorn. If you could just clarify which Stromboli eruption you were looking at, which volcano?
On Stromboli, on Stromboli, yeah. The one you have seen here and heard was one of the craters of Stromboli.
Okay, thank you. Are there any other questions? Did you? Okay. Is there anything online or? Okay, if there are no more questions, you are welcome to approach the panelists after the press conference. And the next one is at 4:30, and it's on the new results of Cassini and the 10th anniversary in Saturn. Thank you all for coming. Thank you very much for the seriously cool presentations that you showed. Thank you.